All right, so today we're going to start a new chapter, and this one's a big one. This chapter 9, it's got like 13 sections in it. It's crazy big. But this semester we're going to break it into two parts. Okay, so you're going to have another exam over the first half of chapter 9 and another exam after over the last half of chapter 9. So we're going to break it into two parts. But it's all about trigonometry. It's all about trigonometry. Sine and cosine. You probably have encountered trigonometry before. Usually you can first encounter it in like high school geometry. And they define sine and cosine in terms of the opposite and the adjacent and the hypotenuse side of a right triangle. We're going to take a little bit of a different approach in this class. We're going to define sine and cosine in terms of the unit circle, which is actually the proper way to define sine and cosine. Okay, it gives you the flexibility to come up with the sine and the cosine for any angle. Whereas if you're just doing right triangle trigonometry, you're limited, right? Because you've only got triangles. The angles of a triangle can't be more than 90 degrees, or at least one. You can have more than one angle of a triangle more than 90 degrees, right? Um, so it gives us a lot more flexibility. Okay, so we actually are going to cover right triangle trigonometry. I think it's in 9.9, I think, but it's well into this chapter on trigonometry. So it's a little different approach than you might be used to. Okay, so we're not going to be using SOHCAHTOA, opposite over adjacent or opposite over hypotenuse, any of that stuff. We're going to define everything in terms of the unit circle. All right, so let's get started. We're first of all just going to, I want to introduce the concept of periodic functions. That's what 9.1 is about, and then we're going to go into sine and cosine. All right, so let's take a ride on a Ferris wheel. We got this Ferris wheel, and so I've got pictures of snapshots of various points that on this Ferris wheel ride. So we board the Ferris wheel down here at the bottom, and so right down here, we board the Ferris wheel, and then the Ferris wheel starts turning in this direction. Okay. So it's turning in the counterclockwise direction. All right. Then it says after 15 seconds we are here. Okay. After 30 seconds we're at the top, and after 45 seconds we're here, which means that probably another 15 seconds, which would be at 60 seconds, we're going to be back to where we started. So that's the idea of periodic functions. They're periodic. They have a period to them. They repeat every periodically, right? So let's graph what this looks like. Right. You're riding this Ferris wheel, and we want to graph your height at any given time, your height above the ground. All right. So at t equals 0, we're at the ground level, so our height is 0. At t equals 15, we're halfway up, right? We've gone a quarter of the way around the circle, but we're halfway up as far as like from our maximum height. All right, so the Ferris wheel is 200 feet in diameter, so we're at 100 feet. Okay, now at 30 seconds, we're all the way at the top, so we're 200 feet up. Okay, and then at 45 seconds, now we've come back down to 100, and then if we can kind of extrapolate from there, assuming that we're going to be rotating at a constant angular velocity, then you would expect that at 60 seconds we're back down to where we started again. Okay, so we've completed one cycle, right? We've completed one cycle, but we're going to go around again, right? We don't want to just go on one loop. We want to go again. So all right, 75 seconds later, we're going to be at 100 again, right? That's 15 seconds after we've left the ground level. So assuming that we're just continuing in the same pattern, at 90 seconds we'll be up at the top again, 200, then we'll be back down at 100, and then finally we'll be back down to the ground again. Okay, so there's two revolutions of this Ferris wheel. All right, so let's graph what that looks like. Now we don't have a lot to go on here. We haven't plotted all the points. We've just plotted, a few of the points here. So, or calculated a few of the points here. So starting at 0, then we're at 100. At 30, we're at 200. At 45, we're back down here. 60, we're at 0 again. And then we just keep going. Every 15 seconds, we're at the points, we get the same points that we were before. Okay, so there's the points that we have. But we've got to try to, if we want to try to sketch a graph, this kind of looks like it's going to be some sort of triangular wave, some sort of sawtooth wave. But let's take a look at this particular point right here. If I look at that point, you can see that the distance from the ground is less than the distance to the the middle here, the 100-foot mark. So we're not moving quite as fast at the beginning. You can see we're basically an eighth around the circle, right? This is like an eighth of the way around the full circle. But even though we're an eighth of the way around, we're not. We haven't traveled. We're I guess angle. As far as angles go, we're the angle here is half of the 90-degree angle, right? So we've traveled 45 degrees, but we're not halfway up as far as the height goes. Okay, so I'm just going to sketch in what this looks like. You have to kind of take my word for it, but it doesn't. It grows slowly at first, and then it grows a little quicker, all right? And then we kind of slow down again. So we get this sort of waveform when we plot this. Okay, so just trying to, it's hard to draw very well with this pen, but you get the idea of what's going on here. It's not some sort of sawtooth wave. It's a nice smooth curve, right? You can imagine riding a Ferris wheel. It's not going to be a jerky ride. It's going to be a fairly smooth ride. Okay, so we have this waveform. All right. So let's talk about some terminology regarding periodic functions. A function is said to be periodic if its values repeat at regular intervals. So there's some sort of cycling going on, right? So let me fill this in. So it's values repeat at regular intervals, Okay, so that's the idea of a periodic function. Now the period of the function, now in your book they describe it as the distance between consecutive peaks. Okay, but really it's just the length of one cycle, right? So you got to figure out, okay, when does one cycle start and the next cycle ends? Okay, so it doesn't have to be the measure between peaks. It's just a measure of one cycle. We could start that cycle anywhere. We could measure the distance between the valleys. Okay, so it's just essentially the length of one cycle. All right, so let's take a look at this this function that this periodic function that we just graphed. What is the period for this function for the height of the Ferris wheel over time? Well, we could use the book definition, and we could measure the distance between consecutive peaks. So here's one peak, here's the other peak. So it's between 30 and 90 seconds. So it appears that the period of this function is 60 seconds. Okay. Now we could have measured the distance between these valleys too, right? Here's another. This is 60 seconds. Okay, 60 seconds. So, so you can see that after 60 seconds, we're back to where we started, and we're just going to continue the pattern over again. So in this particular example, the period is 60 seconds. All right. Midline. Let's talk about midline. What's the midline? The midline is the horizontal line midway between the maximum and minimum values. All right, so what is the midline of this function that we have up here for the height of the Ferris wheel? Okay, so it looks like your maximum is 200 and your minimum is 0. The midway line is this, put a dashed line here through here, is at 100, right? So this is the midline. Okay. So the midline of this Ferris wheel is the line y equals 100. All right. Amplitude, that's another important concept with periodic functions. What is the amplitude? So the amplitude is the vertical distance from the midline to the peak. All right, the vertical distance from the midline to the peak. So let's take a look at our function. What is the amplitude of this function? Midline to the peak. All right, so we're looking at this distance here, right here. Midline to the peak. All right, so our midline's at 100, the peak is at 200, so the amplitude is 100. All right, so the amplitude of this height function for our Ferris wheel is 100 feet. Okay, so it has some units to it in this case because we're the function that we're modeling is height, and it's height in feet. Okay, just like the period has units too, because the horizontal axis is the time axis, and we're measuring time in seconds. Then the period is in seconds. Okay, so really the midline is also 100 feet. It has units as well. All right, so let's take a little closer look at how this function looks. And this video I think is going to get a little long, but I think and some of this is sort of optional. We're going to study some of this stuff in a little more detail, but so here I've got, and it doesn't fit very well on the screen, but I plotted it in a little bit more detail. Here's what the actual heights would be at a little finer resolution for time, right? So I'm doing it every 5 seconds instead of every 15 seconds. Okay, so I have all these heights. So I've measured all these heights. These are all the heights that you would, at every 5 seconds. Okay, and then I've plotted that. So I have a little bit of curve here. You can kind of see what it looks like, a little more detail. So one thing we might ask is, what is the derivative? We could sketch the derivative, right? This is a calculus class, although we're not going to be doing much calculus until the very end of this chapter. But because it is a calculus class, let's take a look at sketching the graph of the derivative. Right? So the derivative is the slope at any point. I like to usually start at the places where the slope is 0. So wherever it changes from increasing to decreasing, it's going to go through 0. So the tangent line is 0 at these points, at 30 seconds and at 90 seconds, right? So it's going to pass through 0 at 30 and 90. It's also going to pass through 0 at 60 and also at 120, right? And at 0. Okay. So next thing, let's look at when it's increasing and when it's decreasing, right? Because we know that when the slope is positive, right? Here, the slope is positive all the way up, okay? So I know that this function is going to be above the x-axis, right? The derivative is going to be above the x-axis. So it's going to go something like this, okay? Now here, the slope is negative, right? Which means the derivative is negative, and the derivative is going to be below the x-axis. So I can sketch that in down here, right? It looks something like that. And then you can see it goes positive again. We have a positive, it's an increasing function. Slope is positive in this segment. Okay? So again, it's going to be above the x-axis. So I'm just sort of sketching it. It's not not a very wiggly lines here. And then in this section here between 90 and 120, it's decreasing again, right? So if we were to plot the derivative would be negative because the slope is negative. And so we're going to have, if I sketch it, it's going to look something like that. Now it should be pretty, so that's a sketch. Okay, not very good, but you can see we get another periodic function, which is interesting. Okay, So the derivative of this periodic function is another periodic function. That kind of makes sense. So if we look at the rate of change of the height and the concavity, you can look between 0 and 15 seconds. Let's look at between 0 and 15 seconds. You can see that it's increasing, and you can see that the slope is becoming more positive. You know, down here we're practically at 0, up here we're more steep. Okay, so between 0 and 15 seconds, the function is increasing. Okay, and it's concave up. All right, let's look at 15 to 30. All right, in this section, let me pick a different color here. In this section, again, we're still increasing, but you can see now the slope is starting to flatten out, right? It's steep, and then it becomes a little less steep. So the slope is decreasing, right? Which means it's concave down. So between 15 and 30, the function itself is still increasing. Okay, but the slope is decreasing, which means it's concave down. All right. Let's look at the next section here. Let's look at between what was it, 30 and 45? So let's look at this section right here. Now you can see it's decreasing, but it's still concave down, right? Because the slope is negative and it's becoming more negative. So more negative is less, so it's decreasing. So the concavity is concave down. So it's decreasing, and is concave down. All right. And then finally, let's look at the section here in the curve between 45 and 60. So you can see it's still decreasing, right? It's still decreasing here. But now it's becoming, less negative, right? It's still negative, but it's less negative. So it's the slope is actually increasing because it's becoming less negative. So in this section, it's decreasing, but it's becoming less negative, so it's increasing, so it's concave up. All right. Okay, so that gives you some properties of this periodic function. All right, so I think that's probably enough for this video, and I will meet you in the next video.